Yes.
Yeah.
Okay, so let's start the next talk. Lawrence Lootens, who's going to give a talk about non-semisimple symmetries from quantum symmetries.
Okay. Thanks for inviting me to talk here. This is a little bit of a different conference than I'm used to, as you will see. I'm not really a CFT person. My background is in lattice models of conformal field theory, but just of quantum many-body systems in general, and looking at the symmetries in these kinds of models. So I'm going to be talking a little bit about some recent work that we did together with Johan Liu, Andras Molnar, Xiaoqi Sun, Frank Verstraeten, who was here last week and gave a lecture about sort of the background for all these things, if you're here, and Kotaro Kato. So the motivation for what I'm talking about here is that in these past few years, there's been quite some progress in understanding what it means to have a symmetry both in continuum theories and in lattice models as well. So I'm going to be focusing on lattice models. So part of the lattice models that have interesting symmetries are precisely those lattice models that are described by some conformal field theory, but I'm not necessarily restricted to that setting per se. So in particular, what people have really started embracing and emphasizing is that symmetries do not need to act in an on-site way. So the setting I'm interested in is where you have some tensor product Hilbert space, some quantum spin chain, some interacting spins. And normally we would say, okay, I have some symmetry, it's described by a group, and it's just some, let's say, some global SU2 symmetry. And this is what we call an on-site symmetry, because you just do a SU2 rotation for every spin, but there's no communication between neighbors. Somewhat recently, people have started generalizing this idea and saying, okay, but what about global symmetries where there is some interaction of the symmetry action between neighboring sites? And in fact, this is what you need if you want to describe something like an anomalous symmetry or one of these non-invertible symmetries. You can prove that these cannot act in an on-site way. There is something intrinsically non-on-site in the way that they are represented in some lattice model. And so, if not described by these sort of tensor products of local operators, then what are they described by? Well, it turns out that there's these kind of objects and tensor network methods, so matrix product operators, and I will define what these are. And they give you the representation theory for these non-on-site symmetries. And so there's been a lot of progress made on that, partly by some people in these rooms, in this room, for systematic constructions of such non-on-site matrix product operator symmetries. And in particular, people have realized that if you think about symmetries as living on the boundary of some higher topological theory, then you can sort of inherit symmetries from that topological theory in your lower dimensional non-topological theory. And since these topological field theories are typically described on the lattice in terms of states of TQFTs, these symmetries then are described by fusion categories or weak Hopf algebras, whichever you prefer. Now, this is all nice, and we can get many interesting models from this. However, it turns out that many physically relevant examples don't seem to fit with this construction. If I go talk to my condensed matter friends, which I have a few, they will give me Hamiltonians that look nothing like those that I get from this sort of TQFT construction. In fact, if you look at the Hamiltonians and the models and the symmetries you get from these TQFT constructions, often they look quite stupid, by lack of a better word. They look very complicated, a little bit, very long range interactions, very strange Hilbert spaces that are not tensor product Hilbert spaces, things like that. And so this is not what we are used to working with in physics. So the topic of this talk is, okay, can we somehow relax these weak Hopf algebra symmetries and ask the question, what is the most general mathematical structure that underlies such an MPO symmetry? So that's kind of the context for this talk. So throughout this whole talk, I will just be using one single example because it's the easiest to explain these things in terms of this example. I will study this particular Hamiltonian. So I have this Hamiltonian here, which is acting on a quantum spin chain of qubits. So my Hilbert space is some tensor product of C2 on n sides. And my Hamiltonian is given by this thing. This is called the Levin-Gu Hamiltonian. It's not really important what its name is. So you have some sums of Pauli X operator. This is the Pauli X here. It's a 2x2 off-diagonal matrix. And then minus Z X Z. So this is some three-body interaction here.
So this is a one-dimensional.
This is a one-dimensional model. This everything I will be talking about is 1 plus 1-dimensional Hamiltonians. For when n is a multiple of 4, this model is actually unitarily equivalent to the XX model. And the XX model is, of course, famously exactly solvable. And it's described by a compact free boson CFT. So everything I'm talking about here has some implication for the XX model, actually. It's just easier to work in this basis for what I will be talking about. And so the symmetry I'm going to be looking at here is the following Z2 symmetry. So it's defined as follows. It's called this CZY symmetry. And it is the product of this two-body operator, the CZ operator. This is called a controlled NOT gate. So this is something that people in quantum information use. It's defined below. It's just some linear combination of Z operators. As a matrix, it's basically 1, 1, 1, minus 1. Should have written it like that maybe, but okay. And then some products of Pauli Z and Pauli X operators. And you can check through explicit computation. It's very, very easy that this operator squares to 1 and that this operator commutes with this Hamiltonian. Okay, good. So this is a symmetry of this Hamiltonian. So it will have some implication on the physics of this Hamiltonian. To give a bit more background of where this symmetry comes from, we didn't just guess the symmetry. In the case of even number of sides, and actually more generally, but that is a bit more complicated, this symmetry can be derived from two U1 symmetries of this model. So we have this so-called momentum and this winding symmetry, which if you know something about free boson CFT, it might be familiar to you as well. On the lattice, these things look like this. So you have these two U1 symmetries. They're compact U1 symmetries. So these generators, they have an integer spectrum. But they don't commute on the lattice. So that's something that's distinct from the continuum theory. There they would commute. Here on the lattice, they don't commute. However, if I look at the Z2 subgroups of these two U1 symmetries, so I just do a pi rotation with using these two generators, I get on the one hand just a global Pauli X. So this is just a global spin flip all the spins. And then here I get this product of this CZ gate together with a Pauli Z operator. And so my symmetry that I'm looking at is basically a Z2 subgroup of the Z2 times Z2 subgroup of these two U1s. And so the symmetry is interesting because it's anomalous. So anomalous means that there is no gap symmetric phase if you have such a symmetry. And this is a reflection of the mixed anomaly between this U1 momentum and the U1 winding of this. So this is kind of the context for this symmetry. And what I want to do is I want to understand the algebraic structure behind this symmetry. Where does this come from? Is there any kind of algebraic structure that I can use to explain this symmetry? So to do that, I will be recasting the symmetry in a slightly different form, namely as this matrix product operator. So what is a matrix operator? This is its definition. If you've never seen this before, it might look maybe a bit complicated, but it's really not very, very, very tricky. So basically what you do is you have your operator and you write it so you choose a basis for the operator. So this is a basis for your domain. This is a basis for the codomain. And then, okay, this is basically just saying which matrix entry am I looking at? And then the coefficient for that is obtained by taking a trace of matrices. That's why it's called a matrix product operator. So it's an operator that's expressed as a product of matrices. This operator here is translation invariant, which is very easy to check. If I replace n by n plus 1, then because of the cyclic property of the trace, I can just cycle all this through. And then to obtain the specific operator that I'm talking about, you have to choose these matrices. I will not really be using this explicit expression. I just wanted to put it there for completeness. So if I do this computation, I will end up with the symmetry operator that I talked about before.
now.
Yes.
Using grass and cats. Do you imagine your vector spaces to be Hilbert spaces?
Yes.
And is the Hamiltonian you consider is itself adjoint?
Yes, it's neat. This is important. I forgot to mention this. So these Pauli matrices, they are self-adjoint. So any linear combination or product of them is self-adjoint as well. And indeed, this is something that will be important because to jump ahead a bit, I will show that the symmetry is non-semi-simple, which is a bit surprising in a Hermitian Hamiltonian. Normally, you don't get these kind of things. There's actually a little bit more symmetry to this Hamiltonian if you put it on open boundary conditions. So if you omit the last term that connects the nth term to the first term, you can insert a generic boundary condition here. So this E1Mn is an arbitrary 2x2 matrix, but okay, because this is a linear map, I can just pick some basis for it, and I just pick the basis of matrix units here. So these operators, there's 4 of these operators, they all commute with my Hamiltonian on open boundary conditions as well. So already I've got 4 operators that commute with my Hamiltonian. And the question is, okay, what is the algebra generated by these operators? Of course, if I have an operator that commutes, then the product of 2 of these operators that both commute will also commute. Is this some kind of closed algebra? I see here that my subscript kind of dropped out on me. That's a shame. These 2 things should be subscripts. But if you take this set of 4 operators that I've defined before for these 4 possible boundary conditions, and you start multiplying them together, you find that this forms a closed algebra. So here, imagine a priori taking A and B to be 1. So if I take A1 times O1 times O1, I will end up with some O0 because I'm defining this A and B to be elements in Z2. So if I take this O1 times another O1, I will get some O0. But this O0 is defined here. And explicitly, again, this thing looks like this, where I have some arbitrary boundary condition now, but now you have to be a little bit careful. This is not a square matrix. So if you look at this here, and you imagine multiplying matrices like this, and then you have to close it at some boundary condition, you can tell that basically only a matrix with entries in this lower little left corner would contribute. So again, there's 4 possible boundary conditions here, bringing the dimension of this algebra up to 8. So this MPOs, they generate an 8-dimensional algebra where the multiplication, the structure constants of this algebra are given by this mu. So again, this is not very important how I get to this point. The thing I mainly want to emphasize is just this is something that's very systematic. You can do this easy. This is very straightforward. Now, what's important here is that this algebra does not depend on the system size here, right? I left this n here explicit, really to say that this is true for any system size. So for any system size, I will get the same symmetry, and that's kind of special. A generic operator that commutes with the Hamiltonian wouldn't have this property, but the fact that this is independent of the system size here, that's something special, and that means that there's some extra structure here. Now, what this extra structure is will become evident. So what I've said before is that, okay, this set of 8 symmetry operators, they form a representation of a 8-dimensional semi-simple algebra, where I'm finding the elements of this algebra basically by choosing these boundary conditions. And then this OA acting on this is the representation of that particular boundary condition with some multiplication mu. Now, apart from just having a multiplication, these matrix products, yes, sorry.
So as this 8-dimensional algebra is the sum of 2 full matrix algebras?
Yeah, I will get to this. But yes, I didn't say this yet, but I talked to you before about
Sum of 8.
Could be.
Yes, so it's semi-simple, so indeed it could be, well, it could be a 2-dimensional matrix algebra plus 4 1-dimensional matrix algebras, or 8 1-dimensional matrix algebras, or 2 2-dimensional matrix algebras. It will be the latter, but I haven't told you enough to see this yet. So these MPOs, they also define some other kind of structure, namely there's an associative co-multiplication here that you can define via this. So if you look at these 2 matrix product operators, you take their tensor product, and you think about this as acting on something in the algebra, tensor the algebra, this defines a co-multiplication. So basically the thing on the right here is well defined, I know what this is. And I can use this thing on the right to define the thing on the left. And the thing on the left here is this co-multiplication acting on this algebra. This has to be true for any n1 and n2. And so in the basis that we're using, it's very easy to see that this thing here is nothing but this, where basically you can think of this as defining these matrix product operators on open boundary conditions and then contracting along this index here, which is going to implement the matrix product in my matrix product operator. All this to say that these matrix operators, product operators, if I choose the basis of my algebra like this, I will get a co-multiplication like this. This co-multiplication is basically the dual of normal matrix multiplication. So the fact that this multiplication is independent on system size, combined with the fact that this co-multiplication is essentially relating matrix product operators on different sizes, implies that this co-multiplication and multiplication, they are compatible, so they satisfy this. And this turns this algebra with the multiplication and co-multiplication into an 8-dimensional bialgebra. I wrote pre-bialgebra there because as an algebra, this thing has a unit, but as a co-algebra, actually, this thing does not have a unit. So the algebra A is unital and it's semi-simple, and it is isomorphic to a direct sum of two-dimensional matrix algebras. But the dual algebra A star is not unital nor semi-simple, since this algebra is basically defined as a direct sum of these two matrix algebras. So one piece is just two-dimensional matrix algebras, but the other piece is basically sort of this corner of a 3x3 matrix algebra. So this is in total, this is an 8-dimensional algebra. But you can see clearly that there's no unit in the dual of this algebra, which means that there's no co-unit in the original algebra. And so this is just what you get if you turn the crank that I just described. So what we're interested in is studying the representation categories of this algebra. So since A is just a nice direct sum of two-dimensional matrix algebras, there's just two simple modules of dimension 2, and we note them as phi1 and phi2. If you have a co-multiplication, you can use it to define a tensor product of these representations as follows. So you can extract fusion rules for these representations. And in this case, we find that any representation times any other representation gives you the sum of your two representations. So this is a little bit weird in the sense that this representation category does not have a unit object. So it wouldn't be fair to call it a monoidal category because you're assuming that there's a unit there. The better name would be semi-monoidal category, or in the EGNO book, they use the term semi-group category. I don't really know what the appropriate name would be. The fact that you don't have a unit is expected because the algebra doesn't have a co-unit. So that's kind of where that is coming from. But other than that, this is a fine semi-monoidal category. It's semi-simple. I can compute associators for this thing. And it's something that turns out to be relevant for this particular lattice model.
Sorry, but what
Yes.
does this imply from this spectrum of the theory? That
I don't know. I don't think it applies anything in particular, or at least I cannot see why having a unit would tell you anything about the spectrum of this Hamiltonian per se. Yeah, I'm not sure. Maybe it's kind of saying that there's no trivial sector for this theory. That's what it's saying. There's no like trivial symmetric sector, which is compatible with the symmetry being anomalous. So indeed, that might be one way of seeing a consequence of this. Yeah, that's a good point.
You can always artificially add the units.
Yes. At the level of the category, I agree. I can just paste it in, but that's not what this algebra is giving me, right? So I don't know how I would have to change the algebra in such a way that
Just has to copy of ground field.
yes, but I don't know how to do that in a way that also preserve the co-multiplication in the way that I want. I think I would have to change my co-multiplication somehow if I wanted to do that. So I agree with you that you can just add it on there, just basically direct sum with the ground field, which is complex numbers in this case, and you would get an additional representation. But to get it to play nicely with the other ones, I think I would have to change the co-product in such a way that it actually changes.
Can you construct fiber functor then? If
Yes.
you add unit, can you construct fiber functor to that?
Sorry, your question is if I have a unit or
Yeah, if you add unit, can you maybe construct fiber factor?
but I have a fiber factor, right? This is I can choose, well, in terms of category, I could choose vec as a modular.
But if category is not without unit, but if category with unit, you have a fiber factor, you can reconstruct Hopf algebra. You would see what is a
Right.
product.
So what I'm not sure about is whether this can be embedded into some bigger dimensional Hopf algebra. I don't think so, because, or at least I don't think so in a way that's completely equivalent to what I have here.
Not Hopf, bialgebra.
Yeah, sorry, bialgebra. So you said bialgebra,
Bialgebra.
right? But that, okay, you're saying.
But if you have a fiber factor, I don't know, if you add unit, and if you can construct a fiber factor,
From my understanding, I already have a fiber factor. Do you need a unit to be able to define a fiber factor? I don't know.
no, but the standard reconstruction.
Because of the co-multiplication, right? So
No, but the standard reconstruction theorem for monoidal categories, for actual monoidal categories. We don't have monoidal category yet.
No, but yes, I don't have a monoidal category.
That's why,
Sure. Yeah. Okay.
for me, it's not a fiber factor.
Okay. Sure.
But if you have a fiber factor, actually, out of category with unit, you can always reconstruct a Hopf.
But I do have a unit, and the co-multiplication does preserve the unit.
it's vector spaces.
Yes.
Quite better.
So okay, like another way of saying it is, but this is my understanding. If this were a fusion category, I could choose vec as a module category. That would, to me, be a fiber factor.
Yes, exactly.
I can do this for this thing.
Mhm.
I can choose vec as a module category, even though it's not monoidal, whatever, it's semi-monoidal. I can find solutions to the module pentagon equation, where the module category is just a single object. That's what I understand as a fiber factor. So I have this in this case. Yeah. Okay.
It's in the
Yes.
formulas, because the product is over.
No, but I was talking about reconstruction.
I mean, like he doesn't have a bialgebra.
There's already co-multiplication and then the product of vectors of representations is just a vector space.
Yeah. That is saying that I have a fiber factor. Yeah, exactly. That's how I understand it as well.
It's already defined.
There's no projection in the co-product or something like that. It is really just taking down the product. That should be clear. I have no clue really what this is, right? So we just did this algebraically. It's very simple to do these computations and see what you get out. I really have no clue what the proper interpretation is. So I'm very happy to hear any opinions on these things. I can also look at the co-representation category, which is equivalent to rep of A star. And this is going to be more complicated because it's non-semi-simple and non-unital. So one thing that you can do is you can unitize this algebra. This is just to look at the representations. I'm not doing this on the whole algebra. It just, if I want to look at the representations of A star, it's easier to unitize it because then there's these theorems about I can find all the projective modules by looking at the regular representation. If you have a non-unital algebra, this becomes a little bit more. So for this unital algebra, you find these 5 different modules. 2 of these are projective, so they're all indecomposable, right? These are indecomposable modules. 2 of these are projective, but not simple. So there's a 3-dimensional one, there's a 2-dimensional one. You can look at whatever the radical, you can look at the top of these things. So this P0 is the projective cover of this S0, this S0 is a simple. P1 is a projective cover of this S1, S1 is a simple. And then this P2, this is a projective module that is simple as well, so it's its own projective. Which, okay, fine, you can do this. These modules, they will still be modules of the non-unitized algebra because it doesn't really change anything. The only thing that happens is that in that case, this S0, which, okay, I'm not telling you, but this S0 is just the module that maps the identity of this unitized algebra to 1 and everything else to 0. If you then also drop the unit, then this becomes the nil module, which is fine. I don't have a unit, so there's no really any priori reason why I couldn't have a nil module there. And then this S1 here, this is really just the thing that maps. I forgot, this is the thing that maps. Yeah, one of these algebras to 1. One of these elements remaining still to 1 and everything else to 0. So if I remove the unit again, okay, then this P0 is no longer projective actually, and then S0 becomes the nil module. But, okay. So proceeding as before, because I have a co-product on the dual algebra, which is the product on my original algebra, I can again take tensor products of representations, and I find these fusion rules. Okay, that you can look at this a little bit. It is not particularly enlightening. The thing that's kind of strange, I guess, is that you're getting this nil module appearing a few times. This is really just to fix the dimension of these modules. So this nil module is a one-dimensional module. Because I'm taking tensor products over vec, the dimensions really just have to multiply. These cannot be some weird quantum dimensions. So this direct sum with the nil module is really just there to fix the total dimension of these things. It's a little bit strange. I don't know if this is the proper way of thinking about it, but it seems consistent. Again, this is just direct computation. There's nothing really deep going on here. And so this is a non-semi-simple monoidal category, and there is a monoidal unit here. That's this psi of S1. So some interesting properties about these things. If I look at rep of A star, so this non-semi-simple category, I can compute the associators of this thing. For a non-semi-simple category, I know this is a little bit tricky, but I'm just ignoring all these morphisms between decomposable modules and the symbols of which they are the predictive covers and all that. So just sort of blindly doing this computation here. You can do this. If you then just restrict to this P0 and P2 module, and you throw out this nil module here, you find that what you're left with is a semi-simple fusion category, vec C2 alpha, where this alpha is the non-trivial element in H3. So this is what people would call the semion category in physics literature. It's something that is known to describe the anomaly of Z2 symmetry. So there's a way to get anomalous Z2 symmetries that are described by this vec Z2 alpha fusion category. So this vec Z2 alpha is somehow contained in this non-semi-simple category in some way.
Semion assumes braiding. Do you have braiding here?
I don't know. I didn't check yet.
There's no natural braid in this.
Well, if I look at my fusion rules, there's certainly there's hope for there being a braiding because they're invariant under like that. I didn't try to compute the braiding yet because it doesn't naturally show up in what we're doing, but I could, and probably there exists one. Indeed, I know this one in particular is modular, right? So there's a braiding and it's even non-degenerate. So I don't know. Maybe it is in there. I'm not quite sure. I haven't computed it yet.
There are two braidings.
Yeah, indeed, but only one of them is modular. I thought there's two braidings on vec C2 alpha, and then one of them is a non-degenerate braiding. The other one is
For the Jocelyn cycle, that's
right. Right. Okay. Anyway, so there should be some way in which this vec C2 alpha is maybe a semi-simplification of this thing that I'm talking about, but I have not properly done that computation. Again, it's all very, very. So the other point, which is related to Christoph's question, this representation category here is semi-simple. It's not monoidal, but it is unitary. So I can define a Hamiltonian that is Hermitian. I have Clebsch-Gordan coefficients basically that are unitary matrices. So I can define Hermitian Hamiltonians that commute with this non-semi-simple symmetry. And the fact that this is unitary also has some implications on basically the renormalisation group properties of these matrix exploit operators. You can show that they are renormalisation group fixed points in that sense that they are invariant under some quantum channel, which is basically conjugating with some unitary Clebsch-Gordan coefficients. So this provides, okay, previously there was some classification of RG fixed point matrix product operators in the context of mixed state topological order, these kinds of things. And this kind of matrix product operators, they give you new solutions to these RG fixed point equations. So to summarize, I argued that by example, that there are symmetries of quantum lattice models that are not described by sort of the previously thought most general description in terms of weak Hopf algebras and the representation categories. And kind of the intuitive reason for this is that if you require your symmetries to come from some higher dimensional topological field theory, you're basically thinking of these symmetries as coming from the topological lines in this TQFT. And these topological lines, they have a lot of nice properties, but they also have properties that actually don't care about if you're just looking at a 1+1D model. Namely, these topological lines, you can really bend them freely as you wish. You can take turns, corners, which is basically what the antipode is giving you in weak Hopf algebra language. But if you're just looking at a 1D chain, you don't care about being able to make corners. So it kind of makes sense that if you're just interested in this 1 + 1D spin chain context, that you need a little bit less assumptions. So more generally, you find that, okay, just given some arbitrary matrix product operator symmetry, and of course the assumption here is that any symmetry of a quantum spin chain can be represented as a matrix product operator. What you can always do is extract this pre-bialgebra structure by basically assuming that the matrix product operator representation is faithful, right? So some open questions regarding this. These kinds of quantum circuit symmetries, namely the ones that I talked about, they're really ubiquitous in physics. This is kind of the language that people in high energy physics use when they talk about lattice models. This is kind of the tools they are using to construct these symmetries, which have some properties that they care about. And this kind of gives you a way to really systematically start going through these symmetries, maybe even classify what these symmetries look like. What they also do is they give you tools for dealing with these symmetries. So for those of you that were here last week, I think Frank talked about duality in quantum spin chains, gauging of these symmetries. And this really all relies on having a detailed algebraic understanding of these symmetries. And the question, well, given that we have now such an algebraic construction for these symmetries, do we know how to gauge these symmetries? The symmetry is anomalous, so you shouldn't be able to gauge it. Can you still gauge that symmetry? There's other kind of non-anomalous symmetries that people know that are not on site, for which people don't know how to gauge them. And this would give you a prescription of doing that. So normally what gauging would require is that you find some symmetric Frobenius algebra in your category, you insert some sort of configuration of like some minimal triangulation in terms of those topological defect lines. That would be the gauged or the orbifold theory. However, if you have this kind of construction that is shorted that you can take, you can basically act with some module filter from one module category to another and implement the gauging in that way. That's something that you can still do in these cases. So there's some questions there. And then finally, something that the kind of things that we do, the things we use these symmetries for relies heavily on Morita equivalence between rep of A and rep of A star. So for a finite dimensional weak Hopf algebra, this is always true. Rep of A and rep of A star are always Morita equivalent. And in fact, you can think of this weak Hopf algebra as arising from some invertible bimodule category between the two. Is there any sense in which this is still true here? So now here, this rep of A here is this semi-monoidal but semi-simple category. Rep of A star is a monoidal category, but it's non-semi-simple. Is there any sense in which the Drinfeld centers, if you can even define it for these two theories, is equivalent somehow? Because that's something that we would need in our constructions.
It looks like you do have natural bimodule.
Yes,
right?
Exactly.
So the question is rep A star the dual category?
Exactly.
The category of antifactors.
Exactly. Yeah. And
Can we check that?
So
Your question is double centralizer property?
Yes.
If centralizer of rep A star is rep A, right?
Yes. But yeah, the first question, if
No, but centralizer has a unit. Oh, but maybe it's a nice way to embed rep A into the unit. So centralizer has a unit.
So it will be just the initialization of the rep.
So there is a maybe bigger category.
So I agree with you that there is a bimodule category here that's given by Vect, and basically the data that I've shown you is literally the data of that bimodule category. There is an additional condition for this bimodule category to be invertible.
Yes.
That's a condition. It's basically
That's what I was just saying.
Okay, sorry, I didn't understand.
Double centralized.
Double centralizer. So we can construct centralizer of rep A star action on vector.
Yeah.
It's naturally has a unit, identity factor.
Yes.
And
So
rep A will
probably
be sitting in
it contains rep A, but it's larger. It contains natural unit.
I see. Okay.
So I think, and this is one is interesting.
I see.
the question is it just adding the unit artificially?
Yeah, maybe something bigger. Maybe something bigger. Yeah.
Yeah,
You have your
Yeah. I mean, again.
But then it should be non-semi-simple kind of Hopf algebra.
Yeah, I get.
Because you're in characteristic 0, right? I mean,
Right.
if one is non-semi-simple, the other has to be non-semi-simple.
Oh,
Yes. I mean,
yeah, but it shouldn't be not just adding unit.
No, in Cartesian zero, it cannot be that,
That you
for
are-
monoidal
you are-
categories, for finite monoidal categories, that one is semi-simple and Marita dual is non-semi-simple. No,
Right.
it's not possible.
Yeah, I see.
So in some sense, rep A is secretly non-semi-simple also. You just have to see it.
Well, okay, again, I'd be very interested in understanding how it works. But these are questions that we actually care about. This is giving you recipes for doing things in lattice models that we could not do before. So it's relevant questions, and that was sort of the point of the talk, is that there are structures that arise here that maybe not obviously are Hopf algebras, maybe they are by the constructions that you're talking about. But it's interesting to look at these things from a different point of view. That was what I wanted to say. Thanks for your attention.
Yeah, there are some questions.
So the RFA category, you just have two simple objects, right? And,
yeah.
And the fusion is very simple. But do you have a fiber factor which is different to what you used, where you just send the simple objects to one-dimensional vector space?
Sorry, one-dimensional.
One-dimensional vector space. Will it still
No, but
be?
then one
Will
times
still
one is
have a
two.
fiber?
No, but 1 times 1 is not,
Oh no, sorry, that wouldn't be compatible with the fusion rules, right? 1 times 1 indeed is
1
1.
times 1 is not 2.
It's not 1 plus 1. 2, but 2 times 2 is 2 plus 2.
Yeah.
So
Yeah, that's why it works for you.
yeah, exactly.
So yeah, okay, I said it wrong, but yeah, can you send it to the direct sum of two copies of vector spaces?
You're saying that maybe they're not simple then anymore, right?
Oh no,
This is what he's doing, yes.
No,
There is some of
sorry,
those.
the question is.
Is rep A star rigid?
I don't know.
Oh,
I don't because
tensor unit is
yeah,
simple.
no, I didn't think about duals.
Tensor unit is simple.
I didn't think about duals.
Oh, but you could try to guess. Like, there are not so many objects.
Now I can look at the fusion rule then. And
Are simples in what?
I'm not sure.
Not rigid, S0.
Model
Zero?
unit
One
here
zero?
would be S1.
Zero is not zero has no dual, right?
No, indeed.
Ah,
Is nil represented?
but isn't Grassenik Verdier?
Sorry,
Isn't Grassenik Verdier?
I have no idea what that means.
It's like weak duality. Weak
I
duality.
have no idea what you mean.
You will get an idea.
No more questions?
No, but rigid answer, no rigid.
No more questions? Yeah.
I think there was a question there.
It was the same question.
Okay.
Okay, so it's on the speaker again.